Learning objectives. In this chapter, the user would learn the following in detail: layered operation, protocol suites, flow and congestion control, multiplexing, synchronization. Flow and congestion control. Congestion. In most networks, there are circumstances in which the externally offered load is larger than can be handled even with optimal routing. Then, if no measures are taken to restrict the entrance of traffic into the network, queue sizes at bottleneck links will grow and packet delays will increase, possibly violating maximum delay specifications. As queue sizes grow indefinitely, the buffer space at some nodes may be exhausted. When this happens, some of the packets arriving at these nodes will have to be discarded and later retransmitted, thereby wasting communication resources. As a result, a phenomenon similar to a highway traffic jam may occur whereby, as the offered load increases, the actual network throughput decreases while packet delay becomes excessive, creating a congestion. It is thus necessary to prevent some of the offered traffic from entering the network to avoid this type of congestion. This is one of the main functions of flow control. Congestion control. Sometimes necessary between two users for speed matching, that is, for ensuring that a fast transmitter does not overwhelm a slow receiver with more packets than the latter can handle. Congestion control is the process for regulating the packet population within the subnetwork. Flow control. A need for flow control arises whenever there is a constraint on the communication rate between 2 points due to limited capacity of the communication lines or the processing hardware. Thus, a flow control scheme may be required between two users at the transport layer, between a user and an entry point of the subnet network layer, between two nodes of the subnet network layer, between two gateways of an interconnected network internet layer. Approaches to flow control. 1. Call blocking. Here, a session is simply blocked from entering the network. Its access request is denied. Such control is needed when the session requires a minimum guaranteed data rate that the network cannot provide due to limited uncommitted transmission capacity. Voice telephone network and circuit switched networks use flow control of this type. A call blocking option is also necessary in integrated voice, video, and data networks, at least with respect to those sessions requiring guaranteed rate. One may admit a session only after a negotiation of some service contract, for example, an agreement on some service parameters for the session's input traffic, maximum rate, minimum rate, maximum burst size, priority level, etc. 2. Packet discarding. When a node with no available buffer space receives a packet, it has no alternative but to discard the packet. Packets may be discarded while buffer space is still available if they belong to sessions that are using more than their fair share of some resource, are likely to cause congestion for higher priority sessions are likely to be discarded eventually along their path and so on. If a packet has to be discarded anyway, it might as well be discarded as early as possible to avoid wasting additional network resources unnecessarily. When some of a session's packets are discarded, the session may need to take some corrective action depending on its service requirements. For sessions where all packets carry essential information, example, file transfer sessions, discarded packets must be retransmitted by the source after a suitable timeout. Such sessions require an acknowledgement mechanism to keep track of the packets that fail to reach their destination. For sessions such as voice or video, where delayed information is useless, there is nothing to be done about discarded packets. In such cases, packets may be assigned different levels of priority, and the network may undertake the obligation never to discard the highest priority packets. These are the packets that are sufficient to support the minimum acceptable quality of service for the session. The data rate of the highest priority packets, the minimum guaranteed rate, may then be negotiated between the network and the source when the session is established. This rate may also be adjusted in real time depending on the congestion level in the network. 3. Packet blocking. When a packet is discarded at some node, the network resources that were used to get the packet to that node are wasted. It is thus preferable to restrict a session's packets from entering the network if after entering they are to be discarded. If the packets carry essential information, they must wait in a queue outside the network, otherwise they are discarded at the source. In the latter case, the flow control scheme must honor an agreement on a minimum guaranteed rate that the session may have negotiated when it was first established. 4. Packet scheduling. In addition to discarding packets, a subnetwork node can exercise flow control by selectively expediting or delaying the transmission of the packets of various sessions. For example, a node may enforce a priority service discipline for transmitting packets of several different priorities on a given outgoing link. A node may also use a possibly weighted round-robin scheduling strategy to ensure that various sessions can access transmission lines in a way that is consistent both with some fairness criterion and also with the minimum data rate required by the session. Finally, a node may receive information regarding congestion further along the paths used by some sessions, in which case it may appropriately delay the transmission of the packets of those sessions. Objectives of flow control. 1. Limiting delay and buffer overflow. For sessions such as voice and video, packets that are excessively delayed are useless. For such sessions, a limited delay is essential and should be one of the chief concerns of the flow control algorithm. For example, such sessions may be given high priority. For other sessions, a small average delay per packet is desirable, but it may not be crucial. For these sessions, network level flow control does not necessarily reduce delay. It simply shifts delay from the network layer to the higher layers. That is, by restricting entrance to the subnet, flow control keeps packets waiting outside the subnet rather than in queues inside it. Flow control avoids wasting subnet resources in packet retransmissions and helps prevent a disastrous traffic jam inside the subnet. Retransmissions can occur in two ways. The buildup of queues causes buffer overflow to occur and packets to be discarded. Snow acknowledgements can cause the source node to retransmit some packets because it thinks mistakenly that they have been lost. Retransmissions waste network resources, effectively reduce network throughput, and cause congestion to spread. Buffer overflow. With buffer overflow, some sessions can capture almost all the buffers and nearly prevent other sessions from using the network. To avoid this, it is helpful to implement a buffer management scheme. In such a scheme, packets are divided in different classes based, for example, on origin, destination, or number of hops traveled so far. At each node, separate buffer space is reserved for different classes, while some buffer space is shared by all classes. Proper buffer management can also help avoid deadlocks due to buffer overflow. Such a deadlock can occur when two or more nodes are unable to move packets due to unavailable space at all potential receivers. Example: two nodes A and B routing packets directly at each other as shown in figure. If all the buffers of both A and B are full packets destined for B and A respectively, then the nodes are deadlocked into continuously retransmitting the same packets with no success, as there is no space to store the packets at the receiver. This problem can also occur in a more complex manner whereby more than two nodes arranged in a cycle are deadlocked because their buffers are full of packets destined for other nodes in the cycle, as shown in figure. There are simple buffer management schemes that preclude this type of deadlock by organizing packets in priority classes and allocating extra buffers for packets of higher priority. Deadlock due to buffer overflow. In A, all buffers of A and B are full of packets destined for B and A, respectively. As a result, no packet can be accepted at either node. In B, all buffers of A, B, C, and D are full of packets destined for C, D, A, and B, respectively. Limited delay and buffer overflow. A typical choice is to assign a level of priority to a packet equal to the number of links it has traversed in the network, as shown in figure. If packets are not allowed to loop, it is then possible to show that a deadlock of the type just described cannot occur. Buffer space for packets that have traveled k links: class n-1, class k, class 1, class 0, class n-1, class k plus 1, class 1, class 0. Buffer space for packets that have traveled k plus 1 links. Figure 6.3. organization of node memory in buffer classes to avoid deadlock due to buffer overflow. A packet that has traveled k links is accepted at a node only if there is an available buffer of class k or lower, where k ranges from 0 to n-1, where n is the number of nodes. Assuming that packets that travel more than n-1 links are discarded as having traveled in a loop, no deadlock occurs. The proof consists of showing by induction, starting with k is equal to n-1, that at each node the buffer of class k cannot fill up permanently. When offered load is large, limited delay and buffer overflow can be achieved only by lowering the input to the network. Thus, there is a natural trade-off between giving sessions free access to the network and keeping delay at a level low enough so that retransmissions or other inefficiencies do not degrade network performance. Flow control should not be exercised at all when network delay is below some critical level, and under heavy load conditions should reject as much offered traffic as necessary to keep delay at the critical level. Neither delay nor throughput can be represented meaningfully by single numbers in a flow control context. Objectives of flow control. Fairness. When offered traffic must be cut back, it is important to do so fairly. The notion of fairness is complicated. However, by the presence of different sessions priorities and service requirements, for example, some sessions need a minimum guaranteed rate and a strict upper bound on network delay. Thus, while it is appropriate to consider simple notions of fairness within a class of similar sessions, the notion of fairness between classes is complex and involves the requirements of those classes. Even within a class, there are several notions of fairness that one may wish to adopt. N-link user, 1 unit per second, n links each with capacity 1 unit per second, single link user 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 1 unit per second. Figure 6.4. Example showing that maximizing total throughput may be incompatible with given equal throughput to all sessions. A maximum throughput of n unit per second can be achieved if the n link session is shut off completely. Giving equal rates of half unit per second to all sessions achieves a throughput of only n plus 1 by 2 units per second. The example in above figure illustrates some of the contradictions inherent in choosing a fairness criterion. There are n plus 1 sessions, each offering 1 unit per second of traffic along a sequence of n links with capacity of 1 unit per second. One session's traffic goes over all n links, while the rest of the traffic goes over only one link. A maximum throughput of n units per second can be achieved by accepting all the traffic of the single link sessions while shutting off the n link session. However, if the objective is to give equal rate to all sessions, the resulting throughput is only n plus 1 the whole divided by 2 units per second. Alternatively, if the objective is to give equal resources to all sessions. The single link sessions should get a rate of n divided by n plus 1 units per second, while the n link session should get a rate of 1 divided by n plus 1 units per second. Layered operation. Computer networks. When two or more computers are interconnected via a communication link, the set of computer stations is called as computer network. The computers can be geographically located anywhere. LAN, local area network. Network in small geographical area, room, building or a campus. MAN, metropolitan area network. Network in a city. WAN, wide area network. Network spread geographically. Country or across globe is called WAN. Network of interconnected networks. Individual wide area networks, WANs, and local networks, LANs, are connected via bridges and gateways. Layer 2. Data link control. Layer. Each point-to-point communication link has data link control modules as per processes at each end of the link. Purpose of data link control is to convert the unreliable bit pipe at layer 1 into a higher level. It collects a bit stream into a frame. Frame is a layer of aggregate of bits. Virtual communication link for sending packets asynchronously but error-free in both directions over the link. The communication at this layer is asynchronous in two ways. First, there is a variable delay between the entrance of a packet into the OLC module at one end of the link and its exit from the other end. Second, the time between subsequent entries of packets into the OLC module at one end of the link is also variable. It takes input into data frames, then it is transmitted sequentially and also process acknowledgement frames sent by receiver. Common networking components that function at layer 2 include network interface cards, Ethernet and token ring switches, bridges. The MAC sublayer. There is a need for an intermediate layer to manage the multi-access link so that frames can be sent by each node without constant interference from the other nodes. This is called medium access control, MAC. It is usually considered as the lower sublayer of layer 2, with the conventional DLC considered as the higher sublayer. Figure below illustrates the relationship between these layers. The service provided by the MAC to the DLC is that of an intermittent synchronous bit pipe. Function of the MAC sublayer is to allocate the multi-access channel so that each node can successfully transmit its frames without undue interference from the other nodes. Virtual Reliable Packet Link, DLC, DLC, MAC, DLC, Virtual Bit Pipe, MAC, Modem, MAC, Modem, Physical Multi-Access Medium. Figure 1.10. Layering for a multi-access channel. The physical medium is accessed by all three users, each of whom hears the transmitted signals of the others. The DLC sublayer sees virtual point-to-point bit pipes below it. The MAC sublayer sees a multi-access bit pipe, and the modems access the actual channel. Layer 3. Network layer. The network layer of the OSI model provides an end-to-end logical addressing system so that a packet of data can be routed across several layer 2 networks. Transport layer ensures the reliable arrival of messages and provides error checking mechanisms and data flow controls, and provides services for both connection mode transmissions and for connectionless mode transmissions. Network layer addresses can also be referred to as logical addresses. The Internet Protocol IP addresses can make networks easier to both set up and connect with one another. The Internet uses IP addressing to provide connectivity to millions of networks around the world. To manage the network and control the flow of packets, many organizations separate their network layer addressing into smaller parts known as subnets. Network layer. When passing packets between different networks, it may become necessary to adjust their outbound size to one that is compatible with the layer 2 protocol that is being used. The network layer accomplishes this via a process known as fragmentation. Two of the additional functions of the network layer are diagnostics and the reporting of logical variations in normal network operation. While the network layer diagnostics may be initiated by any network system, the system discovering the variation reports it to the original sender of the packet that is found to be outside normal network operation. If the calculation done by the receiving system does not match the value sent by the originating system, the receiver discards the related packet with no report to the sender. Retransmission is left to a higher layers protocol. The network layer at a node or site can receive packets from a DLC layer for each incoming link and, in case of a site, from the transport layer. It can send these packets out to the same set of modules. Layer 4. Transport layer. The transport layer provides the functional and procedural means of transferring variable length data sequences from a source to destination host via one or more networks. Shares the transport link between applications. Ensures data reliability. Handles errors and data losses. Supports acknowledged communication via TCP and unacknowledged communications via UDP. Functions of transport layer. The transport layer breaks messages into packets at the transmitting end and resembles packets into messages at the receiving end. Multiplexes several low-rate sessions, all from the same source site and all going to the same destination site, into one session at the network layer. Splits one high-rate session into multiple sessions at the network layer. If the network layer is unreliable, the transport layer might be required to achieve reliable end-to-end communication for those sessions requiring it. End-to-end flow control is often done at the transport layer. Layer 5, the session layer, manages multiple applications and maintains synchronization points. This layer provides the transport layer with the information needed to establish the session. This layer would be an appropriate place to achieve load sharing between many processors that are sharing computational tasks within a network. Also, deals with access rights in setting up sessions. Functions handles the interactions between the two endpoints in setting up a session. Virtual connection between application entities. Synchronization of data flow, creation of dialog units, and connection parameter negotiations. Partitioning of services into functional groups. Acknowledgements of data received during a session and retransmission of data if it is not received by a device. Layer 6, Presentation Layer. The presentation layer is responsible for how an application formats the data to be sent out onto the network. The presentation layer basically allows an application to read or understand the message. Functions of a presentation layer: encryption and decryption of a message for security, compression and expansion of a message so that it travels efficiently, graphics formatting, content translation, system-specific translation, encrypt data, network, decrypt data. Layer 7, the application layer. The application layer provides an interface for the end user operating a device connected to a network. This layer is what the user sees in terms of loading an application such as web browser or email. That is, this application layer is the data the user views while using these applications. Functions: support for file transfers, ability to print on a network, electronic mail, electronic messaging, browsing the World Wide Web. Multiplexing. Multiplexing means that a system resource is shared among multiple users. A single physical CPU is shared, multiplexed, among multiple jobs, each of which believes it has its own private processor. Data being sent by multiple users can be multiplexed over the physical links that make up a network. The three hosts on the left side of the network, L1 to L3, are sending data to the three hosts on the right, R1 to R3, by sharing a switched network that contains only one physical link. Three flows of data corresponding to three pairs of hosts are multiplexed onto a single physical link by switch 1 and then demultiplexed back into separate flows by switch 2. Multiplexing multiple logical flows over a single physical link. Methods of multiplexing: synchronous time division multiplexing, STDM, frequency division multiplexing, FDM, synchronous time division multiplexing, STDM. The idea of STDM is to divide time into equal sized quanta and, in a round-robin fashion, give each flow a chance to send its data over the physical link. During time quantum 1, data from the first flow is transmitted. During time quantum 2, data from the second flow is transmitted, and so on. This process continues until all the flows have had a turn, at which time the first flow gets to go again and the process repeats. Frequency division multiplexing (FDM). The idea of FDM is to transmit each flow over the physical link at a different frequency, much the same way that the signals for different TV stations are transmitted at a different frequency on a physical cable TV link. Limitations of SDTM and FDM. If one of the flows, host pairs, does not have any data to send, its share of the physical link, that is, its time quantum or its frequency, remains idle, even if one of the other flows has data to transmit. Both STDM and FDM are limited to situations in which maximum number of flows is fixed and known ahead of time. It is not practical to resize the quantum or to add additional quanta in the case of STDM or to add new frequencies in the case of FDM. Statistical multiplexing. It is like STDM in that the physical link is shared over time. First, data from one flow is transmitted over the physical link, then data from another flow is transmitted, and so on. Unlike STDM, data is transmitted from each flow on demand rather than during a predetermined time slot. If only one flow has data to send, it gets to transmit that data without waiting for its quantum to come around, and thus without having to watch the quanta assigned to the other flows go by unused. It is this avoidance of idle time that gives packet switching its efficiency. It has no mechanism to ensure that all the flows eventually get their turn to transmit over the physical link. Defines an upper bound on the size of the block of data that each flow is permitted to transmit at a given time. This limited size block of data is typically referred to as a packet to distinguish it from the arbitrarily large message that an application program might want to transmit. As a packet switched network limits the maximum size of packets, a host may not be able to send a complete message in one packet. The source may need to fragment the message into several packets, with the receiver reassembling the packets back into the original message. Each flow sends a sequence of packets over the physical link, with the decision made on a packet by packet basis as to which flow's packet to send next. Notice that if only one flow has data to send, then it can send a sequence of packets back to back. However, should more than one of the flows have data to send, then their packets are interleaved on the link. Statistical multiplexing defines a cost-effective way for multiple users, example, host-to-host flows of data, to share network resources, links and nodes, in a fine-grained manner. It defines the packet as the granularity with which the links of the network are allocated to different flows, with each switch able to schedule the use of physical links it is connected to on a per packet basis. The decision as to which packet to send next on a shared link can be made in a number of different ways. For example, in a network consisting of switches interconnected by links, the decision would be made by the switch that transmits packets onto the shared link. Each switch in a packet switched network makes this decision independently on a packet by packet basis. A switch could be designed to service packets on a first in first out FIFO basis. Another approach would be to service the different flows in a round robin manner, just as in STDM. This might be done to ensure that certain flows receive a particular share of the link's bandwidth, or that they never have their packets delayed in the switch for more than a certain length of time. A network that allows flows to request such treatment is said to support quality of service QoS. Figure: a switch multiplexing packets from multiple sources onto one shared link. In figure, since the switch has to multiplex 3 incoming packet streams onto one outgoing link, it is possible that the switch will receive packets faster than the shared link can accommodate. In this case, the switch is forced to buffer these packets in its memory. Should a switch receive packets faster than it can send them for an extended period of time, then the switch will eventually run out of buffer space and some packets will have to be dropped. When a switch is operating in this state, it is said to be congested. Challenges: fairly allocating link capacity to different flows, dealing with congestion when it occurs. Protocol suites. Protocol, conventions and rules associated with the communication between two entities. Internet Protocol Suite is the computer networking model using a set of communication protocols. TCP/IP Protocol Suite, Transmission Control Protocol (TCP) and the Internet Protocol (IP) is the most common networking protocols. Open System Interconnection (OSI) Protocol Suite, comprised of numerous standard protocols that are based on the OSI reference model. OSI Protocol Suite, designed for communication between hardware and software systems despite differences in underlying architectures. Implemented by ISO, International Organization for Standardization, and International Telecommunication Union, Telecommunication Standardization Sector, ITUT. Figure: the OSI protocol suite maps to all layers of the OSI reference model. OSI physical and data link layers. The OSI protocol suite supports numerous standard media access protocols at the physical and data link layers. The wide variety of media access protocols supported in the OSI protocol suite allows other protocol suites to exist easily alongside OSI on the same network media. Supported media access protocols include IEEE 802.2 LLC, IEEE 802.3, Token Ring or IEEE 802.5, Fiber Distributed Data Interface FDDI, and X.25. OSI Network Layer. OSI protocol suite specifies two routing protocols at the network layer: N system to intermediate system ESIS, intermediate system to intermediate system ISIS. OSI suite implements two types of network services: connectionless service, connection-oriented service. OSI connectionless network service, implemented using Connectionless Network Protocol (CLNP) and Connectionless Network Service (CLNS). CLNP and CLNS are described in the ISO 8473 standard. CLNP: OSI network layer protocol that carries upper layer data and error indication over connectionless links. Provides the interface between the connectionless network service CLNS and upper layers. CLNS provides network layer services to the transport layer via CLNP. Does not perform connection setup or termination because paths are determined independently for each packet that is transmitted through a network. This contrasts with the Connection Mode Network Service CMNS. CLNS provides best effort delivery, which means that no guarantee exists that data will not be lost, corrupted, misordered, or duplicated. Relies on transport layer protocols to perform error detection and correction. OSI Connection-Oriented Network Service, implemented by using the Connection-Oriented Network Protocol (CONP) and Connection Mode Network Service (CMNS). CONP: an OSI network layer protocol that carries upper layer data and error indications over connection-oriented links. Based on the X.25 Packet Layer Protocol (PLP) and is described in the ISO 8208 standard X.25 Packet Layer Protocol for DTE. Provides the interface between CMNS and upper layers. Network layer service that acts as the interface between the transport layer described in the ISO 8878 standard. CMNS performs functions related to the explicit establishment of paths between communicating transport layer entities. These functions include connection setup, maintenance, and termination, and CMNS also provides a mechanism for requesting a specific quality of service QoS. This contrasts with CLNS. OSI protocols transport layer. The OSI protocol suite implements two types of services at the transport layer: connection-oriented transport service, connectionless transport service. 5 connection-oriented transport layer protocols exist in the OSI suite, ranging from Transport Protocol Class 0 through Transport Protocol Class 4. Connectionless transport service is supported only by Transport Protocol Class 4. Transport Protocol Class 0 TP0. The simplest OSI transport protocol performs segmentation and reassembly functions. Transport Protocol Class 1 TP1 performs a segmentation and reassembly and offers basic error recovery. sequences protocol data units PDUs and will retransmit PDUs or reinitiate the connection if an excessive number of PDUs are unacknowledged. Transport Protocol Class 2 TP2 performs segmentation and reassembly as well as multiplexing and demultiplexing data streams over a single virtual circuit. Transport Protocol Class 3 TP3 offers basic error recovery and performs segmentation and reassembly in addition to multiplexing and demultiplexing data streams over a single virtual circuit. Also, sequences PDUs and retransmits them or reinitiates the connection if an excessive number are unacknowledged. Transport Protocol Class 4 TP4 TP4 offers basic error recovery, performs segmentation and reassembly, and supplies multiplexing and demultiplexing of data streams over a single virtual circuit. Sequences PDUs and retransmits them or reinitiates the connection if an excessive number are acknowledged. Provides reliable transport service and functions with either connection-oriented or connection-less network service based on the Transmission Control Protocol TCP in the Internet Protocol Suite. OSI Protocols Session Layer. The session layer implementation of the OSI Protocol Suite consists of Session Protocol and Session Service. Session Protocol. The Session Protocol allows Session Service users SS users to communicate with the Session Service. An SS user is an entity that requests the services of the session layer. Such requests are made at Session Service Access Points SSAPs, and SS users are uniquely identified by using an SSAP address. Session protocol is defined in the ISO 8327 standard and in the ITU-T X.225 recommendation. A connectionless version of the session protocol is specified in the ISO 9548 standard. OSI protocols session layer. Session service. Session service is defined in the ISO 8326 standard and in the ITU-T X.215 recommendation. Provides 4 basic services to the SS user. Establishes and terminates connections between SS user and synchronizes the data exchange between them. Performs various negotiations for the use of session layer tokens which must be possessed by the SS user to begin communicating. Inserts synchronization points in the transmitted data that allow the session to be recovered in the event of errors and interruptions. Allows SS users to interrupt a session and resume it later at a specific point. Figure shows the relationship between the SS user, the SSAP, the session protocol, and the session service. OSI protocols presentation layer. The presentation layer implementation of the OSI protocol suite consists of a presentation protocol and a presentation service. Presentation protocol allows presentation service users PS users to communicate with the presentation service. A PS user is an entity that requests the service of the presentation layer. Such requests are made at presentation service access points (PSAPs). PS users are uniquely identified by using PSAP addresses. The OSI presentation protocol is defined in the ISO 8823 standard and in the ITU-T X.226 recommendation. A connectionless version of the presentation protocol is specified in the ISO 9576 standard. Presentation service negotiates transfer syntax and translates data to and from the transfer syntax for PS users, which represent data using different syntaxes, used by two PS users to agree upon the transfer syntax that will be used. When a transfer syntax is agreed upon, presentation service entities must translate the data from the PS user to the correct transfer syntax. The OSI presentation layer service is defined in the ISO 8822 standard and in the ITU-T X.216 recommendation. OSI protocols application layer. The application layer implementation of the OSI protocol suite consists of various application entities. An application entity is the part of an application process that is relevant to the operation of the OSI protocol suite. An application entity is composed of the user element and the application service element ASE. TCP/IP protocol suite. The TCP/IP protocol suite maps to a four-layer conceptual model known as the DARPA model, which was named after the US government agency that initially developed TCP/IP. The four layers of the DARPA model are application, transport, internet, and network interface. Each layer in the DARPA model corresponds to one or more layers of the 7-layer OSI model. Network interface layer. The network interface layer, also called the network access layer, sends TCP/IP packets on the network medium and receives TCP/IP packets of the network medium. TCP/IP was designed to be independent of the network access method, frame format, and medium. TCP/IP can be used to communicate across different network types that use LAN technologies such as Ethernet and 802.11 wireless LAN and WAN technologies such as frame relay and asynchronous transfer mode ATM. The network interface layer of the DARPA model encompasses the data link and physical layers of the OSI model. Internet layer. The TCP/IP protocol suite has two sets of protocols at the internet layer. The IPv4, also known as IP, is the internet layer in common use today on private intranets and the internet. IPv6 is the new internet layer that will eventually replace the existing IPv4 internet layer. The internet layer responsibilities include addressing, packaging, and routing functions. The internet layer is analogous to the network layer of the OSI model. The core protocols for the IPv4 Internet layer consist of the following. The Address Resolution Protocol (ARP) resolves the Internet layer address to a network interface layer address, such as a hardware address. The Internet Protocol is a routable protocol that addresses, routes, fragments, and reassembles packets. The Internet Control Message Protocol (ICMP) reports errors and other information to help you diagnose unsuccessful packet delivery. The Internet Group Management Protocol (IGMP) manages IP multicast groups. The core protocol for the IPv6 Internet layer consists of the following. IPv6 is a routable protocol that addresses and routes packets. The Internet Control Message Protocol for IPv6 ICMPv6 reports errors and other information to help you diagnose unsuccessful packet delivery. The Neighbor Discovery (ND) protocol manages the interactions between neighboring IPv6 nodes. The Multicast Listener Discovery (MLD) protocol manages IPv6 multicast groups. Transport Layer. The transport layer, also known as the host-to-host transport layer, provides the application layer with the session and datagram communication services. The transport layer encompasses the responsibilities of the OSI transport layer. The core protocols of the transport layer are TCP and UDP. TCP and UDP operate over both IPv4 and IPv6 Internet layers. TCP provides a one-to-one connection-oriented, reliable communications service. TCP establishes connections, sequences, and acknowledges packets sent and recovers packets lost during transmission. UDP provides a one-to-one or one-to-many connectionless, unreliable communications service. UDP is used when the amount of data to be transferred is small, such as the data that would fit into a single packet, when an application developer does not want the overhead associated with TCP connections, or when the applications or upper layer protocols provide reliable delivery. Application layer. The application layer allows applications to access the services of the other layers, and it defines the protocols that applications use to exchange data. The application layer contains many protocols, and more are always being developed. The most widely known application layer protocols help users exchange information. The Hypertext Transfer Protocol (HTTP) transfers files that make up pages on the World Wide Web. The File Transfer Protocol (FTP) transfers individual files, typically for an interactive user session. The Simple Mail Transfer Protocol (SMTP) transfers mail messages and attachments. The following application layer protocols helps user and manage TCP/IP networks. The Domain Name System (DNS) protocol resolves a host name such as www.microsoft.com to an IP address and copies name information between DNS servers. The Routing Information Protocol (RIP) is a protocol that routers use to exchange routing information on an IP network. The Simple Network Management Protocol (SNMP) collects and exchanges network management information between a network management console and network devices such as routers, bridges, and servers. Synchronization. The main function of Layer 5 session layer is synchronization. It is to provide a way for the session users to establish connections called sessions and transfer data, possibly using half duplex over them in a safe and orderly manner, even if the end computers fail and reboot. This is necessary because though the transport layer can recover from network layer intermediate node failures, it cannot always recover from some problems if an end computer fails and reboots. On transferring a database file from one end computer to another, an acknowledgement is sent back. Unfortunately, this can happen before the destination application has written the received data to disk. If the destination transport layer reboots, it will receive a restart request from the source. But since the source thinks it knows how much data has been received at the destination, it will not bother to resend it. The problem is that the two end applications do not handshake that the data sent got completely handled by the destination application. This is called synchronization. Session layer allows a process to add checkpoints which are considered as synchronization points into a stream of data. Example, if a system is sending a file of 800 pages, adding checkpoints after every 50 pages is recommended. This ensures that 50-page unit is successfully received and acknowledged. This is beneficial at the time of crash, as if a crash happens at page number 110, then there is no need to retransmit 1 to 100 pages. Conclusion. In this chapter, we have covered the following in detail: layered operation, protocol suites, flow and congestion control, multiplexing, synchronization.